Hi everybody, welcome back to the Feynman technique. Today we'll be taking a look at this really nasty integral, but we're going to be making use of that universal Mellon-Barnes formula that I derived in my last video and my second to last video. So let's go ahead and get started. Let's see. I don't like these powers here. Let's try to reduce the power here by cutting it in half. We're going to let u equal x squared. Well, this implies that du is equal to 2x dx. Let's bring that down there. And of course, our x is going to be square root of u. We will write this 1 over square root of u as u to the 1/2 du. 1/2 u to the 1/2 du is equal to dx. Let's plug that in. All right. Well, our x is square root of u. Okay, let's see. Our x to the 4th is just going to become a u squared. This is just going to become a u. And our dx is this. Now, it looks a lot messier now. But let's see what we can do. Of course, we can bring this 1/2 outside. Let's see, natural log squared of u. I believe we can take this square root out as a 1/4. And now it's going to become a 1/8. All right, so we're looking somewhat better. Not much. But let's go ahead and delete this substitution step and bring our dummy variable back to x. Okay. There we go. All right, now let's work with this. So what I would like to do, now this is going to get extremely messy. I am going to be utilizing integral calculator. No, probably not. I am going to be utilizing artificial intelligence to do some of the really messy calculations that, we'd all be able to do. But it would just take a long time, and you don't want to see me do that. So let's see, what can we do? It's not time to create our function of t yet. Let's see, let's notice this. Let's notice that x squared minus x plus 1 times x plus 1 is just x cubed plus 1. All right, not hard to show that. So let's go ahead and rewrite this using that. Let's go ahead and multiply the top and the bottom by x plus 1. Now, doing that, of course, we will just get x cubed plus 1 in the denominator. All right, and now it's time to break this up into two separate integrals. All right, I should be labeling this I. I is equal to this, I is equal to this, and I is equal to this. So let's split this up, like I said, into two separate integrals. One is going to have just that factor of 1 in it, and the other is going to have this x in it. So combining the x and the x to the 1/2, we will just get x to the 3/2. All right, and now let's see. I think we're ready for our f of t. We're going to let some f of t be equal to more or less just one of these integrals, except we're just going to have x to the t. All right. Now, if you know, you'll notice if you take two derivatives with respect to t using the Leibniz rule for differentiation, your first derivative, you'd be taking the derivative with respect to t of this, which would just give you x to the t times natural log x. Taking another derivative would simply give you natural log squared of x. So we can say that f double prime of t is equal to this. All right, that means our original integral I is going to be equal to 1/2 f double prime evaluated at 3/2, and where I got that was right here. This is our, oh, not 1/2, this is 1/8. You see, we do actually have f double prime at 3/2, 1/8. We have 1/8 of f double prime where t is 3/2. But now we need to take care of this part. That's just going to be f double prime at 1/2 plus f double prime at 1/2. Oh yeah, and of course 1/8. Yeah. All right, so now if we can just get this into an explicit form, an explicit function of t not involving an integral, we take two derivatives and figure it out like this. Now this is obviously, this is the hard part. So what we're going to do is we're going to make use of one of these formulas. So this formula I derived in my previous video. However, we don't need that formula exactly. I think what we need is actually this formula. This formula right here will suffice. What was that formula? It was this. So I'm just going to copy that right there. All right, so now you'll notice that this integral is in this form with our a being equal to t and our b being equal to 3. So we can say that this is true. If we plug in t for a, t for a, we get this, and then if we plug in 3 for b, we get this. Great. All right, so now we have f of t just being equal to this. And you see we actually gained some extra parts over here. Our f of t expressed as an integral only contained this part. And that's due to the convergence of the integral based on the value of t. However, our f of t is actually going to converge for many more values of t since sine is cyclical. So, okay, anyway. Let's see, where was I going? Okay, so yeah, now we need to take two derivatives of this thing. And I'm going to use online derivative calculator for that. We're going to say f double prime of t is equal to, let's see, let's go into our derivative calculator with steps. We will plug in this function and we will differentiate with respect to t once. And that's pretty messy. And then we will calculate one more derivative. And the good thing about this is it puts it in more or less its simplest form. So we're going to have this. So let's go ahead and copy this. So f double prime of t is equal to this. And just to make sure that it got it correct, what I'm going to do is I'm just going to call this f2 of t and then put two derivatives with respect to t in front of there. Okay, so it didn't like something here. Oh, it doesn't like this sign cubed. So we're actually going to have to put that cubed outside like this. Cubed. Okay, and then make sure this purple integral matches up with this one, and it does. All right, so online derivative calculator successfully evaluated f double prime at t, and you can see why I want to use that online integral calculator. Of course, I'm sorry, derivative calculator. We could take two derivatives of this thing with respect to t. Taking derivatives is a fairly mechanical process as long as you don't make any mistakes. But you don't want to see me do that. I know you all could do that, and you know I could do that with enough time. So I just skipped all that and went right for the derivative calculator. So there's our f double prime of t. So now we're done. So I is equal to this. So we have 1/8 and then f double prime where t is 3/2. So t is 3/2. Again, t is 3/2 and t is again 3/2. All right. And then for our second one, we're doing the exact same thing, except we're plugging in 1/2 for t. So t is 1/2, t is 1/2, and t is 1/2, and that is perfect. So now what I'm going to do is I'm going to pause the video and I'm going to clean this. I'm going to clean this expression up right here because that is just ridiculously messy. All right, so I'll be right back. All right, so cleaning up these expressions inside our trig functions, I've now gotten it to this. All right, we can go further. I'll be right back with the next step. All right, and after doing all the algebra and trigonometry on that, we arrive at a final expression of 5 pi cubed over 72. So let's just state that. Where's our integral? And this is equal to 5 pi cubed over 72. All right, guys, I hope you enjoyed that, and we will see you next time.